Hello everybody, welcome to the lecture for today, April 10th, not March 10th. Today I want to take a beat from what we've been talking about in the previous lectures, and just review them. We moved through them pretty quickly. It was just one section, but there's a lot that's in that section, and I want to make sure that we're all on the same page moving forward. So today we're just going to review the things that we've talked about up until now, with permutations, and maybe do a few computations. We'll see. So what's the idea? The idea was that we introduced the notion of a group. And I'm not going to write down all the group axioms, but morally speaking, so this is a definition in quotations, a group is a set with a multiplication that looks like matrix multiplication. So in particular, when I multiply two things, they don't necessarily have to commute. It has to be associative, so it doesn't matter where the order in which the way that I group things with the parentheses. The order matters, but the grouping doesn't. So I can do things like take powers of a group element, just like I can take powers of a matrix by multiplying itself by itself over and over again. I need an identity element, like the identity matrix, so it has to be a square matrix multiplication. Elements need inverses, so this is for this is on invertible n by n matrices. And so the thing that we talked about mainly is this symmetric group, or the permutation group. So this is the set of bijections. I'm going to call them self-bijections on 1 up through n. So it's the way that I can map this set, into itself. So for example, you might have the set 1, 2, 3, 4, and 1 might get mapped to 2, 2 might get mapped to 4, 4 might get mapped to 3, and 3 might get mapped to 1. This is an example of an element of the permutation group. So the first thing we proved is that every permutation, every self-bijection, has a cycle structure. I'm going to call this the cycle theorem. Every permutation is the product of disjoint cycles. This presentation is unique. This is unique up to rearrangements of the cycles. Right, so here disjoint means that the cycles don't share any numbers in common. And what's a cycle? Well, we introduced this fun notation. Let's write this one as a cycle. 1 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes to 1. So this one is already just one cycle of length 4. But in general, if you have S of 1,000, maybe you have a cycle of length 500, a cycle of length 200, and a cycle of length 300. You can have your cycle structure. You can have lots and lots of cycles, and they can be sigma may have cycles of length. What did I write here? Length. 200, 100, 100, 100, and 500. For example. And you can add, this list can be as long as you wish. They all just need to add up to the number of things in your space. And the way, and you did this on your homework, the way in which we find the cycle structure of a permutation is just by trying to put every element in a cycle. So I put one in a cycle, and then I would look for the first element that's not in a cycle already and try to find a cycle containing that one. And eventually, every element gets put into one of these cycles. And we consider fixed point cycles of length 1. So every point gets put inside of some cycle. Okay, so what else do we have? We have order. So let G be a group. And little g be an element of big G. So if this is the permutation group, little g is a permutation. Otherwise, little g is just some element of the group, capital G. The order of G, written little o of G, is the smallest n such that G to the n is equal to the identity element, where E is the identity element of G. This notation, this preservation of the you hold the symbol E usually always to represent the identity element of a group G. So not every element will have an order in an arbitrary group. For instance, if you take the group of integers, right, I can add and subtract integers. So for the integers, the group operation is multiplication, is addition. Then no element has an order, because if I start adding some non-zero element to itself again and again, it just escapes to infinity or plus infinity or minus infinity, right? It just marches. 1, 2, 3, 4, or 3 plus 3 is 6, plus 3 is 9, 12, 15. It can never get back to the identity element of the additive group of integers, which is 0. So not every element in an arbitrary group has an order, but every element of a finite group has an order. A finite group has an order. Furthermore, I mean, we proved this in 2 separate theorems, but for the symmetric group, the order is the least common multiple of the lengths of the disjoint cycles. And you can think about this as sort of in the following way, intuitively at least. Right, let's say that I have a cycle of length 3 and a cycle of length 4. Now, what do I want to happen? What I want to happen is that when I start iterating the permutation, right, I have 7 elements. I've arranged these 7 elements in a very special way so that they fit into these 2 cycles. But in general, if I were to list, if they were numbers, for instance, they wouldn't need to be listed in this nice order. They could be interchanged with one another. So the idea is that I want to find the times when all 7 numbers are back to their original position, right? If I start taking sigma, right, this represents the map sigma. Sigma to the n, sigma squared, sigma squared, sigma cubed, and so on and so forth. So I want to find the power of sigma such that all these numbers are taken back to themselves. And what you'll notice is that this one needs to take a complete turn, and this one also needs to take a complete turn. So these things will have a make a complete cycle if the iterative sigma is a multiple of 4, right? Because for this one to go back to itself, it needs to go 1, 2, 3, 4, and then again 4 more times and 4 more times. So any multiple of 4 will in fact take all these elements back to themselves, and any multiple of 3 will take all of these things back to themselves. So the only way for the power of sigma to be the identity transformation on every element of this 7-element set is for it to be both a multiple of 3 and a multiple of 4, which means it has to be a multiple of 12. Right? The least common multiple of the order here and the order here will work. So it's kind of interesting to think, if you're familiar with music or musical notation, right? This is moving forwards in triplets, and this moving forward in quadruplets. So I want to find the downbeat, which means that that's not quite right either. Right? I want to imagine a song moving forward in 3/4 time and 4/4 time, and then I want to find the times when both of these songs will be hitting a downbeat if they're moving at the same pace with their quarter notes. Okay, sorry, that analogy got a little bit garbled. So what do I want to do? I just want to do a few other examples of computations with order. So let's find one more order. So here's a product of 3 cycles. They're not disjoint cycles, so the first thing I need to do if I want to find the product of these things is to put them as a product of disjoint cycles. So this is sort of 2 problems in one. So let's put 1 into a cycle. Remember, these are compositions of functions, right? I can call this sigma 1, sigma 2, and sigma 3. So this is sigma 1 of sigma 2 of sigma 3. And if I want to see where 1 goes, 1 first goes into sigma 2 and is fixed. The output of sigma 3 of 1 is just 1. The output of sigma 2 of 1 is just 1. So the output of sigma 1 of 1 is 2. So 1 still goes to 2. 2 is fixed under sigma 3. 2 goes to 4 under sigma 2. And then it's fixed under sigma 1. 4 is fixed under sigma 3. 4 goes to 5 under sigma 2. And then it's fixed under sigma 1. 5 goes to 6 under sigma 3, and then it's fixed. 6 goes to 7, and then it's fixed, because 7 doesn't appear here, it's not moved. 7 goes to 8, and then 8 goes to 5, 5 goes to 2, 2 goes to 3. 3 is fixed, 3 is fixed, 3 goes to 1. I've closed up my cycle. So this product of 3 cycles, one is length 3, one is length 3, the other is length 4, is a cycle of length 8. And the order is therefore 8. The order of a cycle is just its length. So find the order of 1, 2, 3, 4, 5, 6, 7, 8, 9. So here I have a cycle of length 2, a cycle of length 3, and a cycle of length 4. And to find the order, I just take the least common multiple of each of these things, right? So I have 2, 3, the least common multiple of these is 6. 6 and 4 gives me 12. 12 is a number that's an order of each of these cycles, which is, it's the smallest number, which is an order of all of these, right? 12 is a multiple of 2, so it's this one get 1 and 2 get back to each other. 12 is a multiple of 3, and it's a multiple of 4. So this is the procedure for finding order. Okay, the last theorem that we proved recently is about the sign. So there's a few different ways to define the sign, and they're all equivalent. So the practical way, there's a formal way where you actually know it's well defined from the start, and then you prove that it's not the way that I'm about to define it now will also be well defined, but it's easier to prove properties of the sign when it's defined the other way. But let's do the practical way, which is to just read it from the cycle structure again. So let sigma be a permutation which is the product of cycles of length L1, L2, Lm. Of disjoint cycles, sorry. Actually, the disjointness doesn't matter here, believe it or not, but usually when we write a permutation, we always want to bring it to cycle notation, because this is the easiest to think about and work with, more often than not. The sign of sigma is, well, we write it down as the sign of sigma. This is minus 1 to the L1 plus 1 times minus 1 to the L2 plus 1 times minus 1 to the Lm plus 1. Okay, so it's either equal to plus or minus 1, always. And let's do a quick example. The sign of 1, 2 times 2, 3, 4, 3, 4, 5, sorry, is minus 1. The length here is 2, so it's 3, times minus 1. Length here is 3, so this is 4. So this is minus 1. So far we haven't seen why the sign is useful, but there are two things I'd like to point out now. So a few of them that I pointed out when the book covers, and the last one is a connection with matrices. So the important thing is, I'll just call this the sign properties theorem. These are the important things about signs. So the sign of the identity transformation is just 1. Here's the really important thing. The sign of the product of two permutations, I don't even need them to commute, is the product of the signs. The sign of the inverse of a transformation is just the sign of the original one. And finally, the sign of a transposition, KL, so a cycle of length 2, is always -1. So another way to think about the sign is -1 if sigma is the product of an odd number of transpositions, and +1 if it is the product of an even number of transpositions. Right, so for instance, 1, 2 times 3, 4, 5 is 1, 2 times 3, 4 times 4, 5. You proved in your homework that you can split this one up as 3, 4 times 4, 5. Or vice versa. I can't remember the order. But you can always write it as a proposition. Or as the product of two transpositions. Right, so this is the product of 3 transpositions. So I need because it's 3 transpositions, the sign is -1. And the remarkable thing about the sign, and this is this property that's driving it, is that it doesn't matter how I break the way that I write something as a product of transpositions is not unique. So no matter how I try to write my original permutation as a product of transpositions, the sign will always be the same. I will either always need an even number of transpositions or always need an odd number of transpositions. So for instance, you can use this to tell whether two permutations are different, right? Let's say that I have a product of 10,000 transpositions and a product of 1,501 transpositions. In general, it would be very hard to prove. If it was 10,000 and 1,500, it would be very difficult to actually compute out the cycle structures and see whether these were equal. But if I know that it's a product of different number of transpositions, then I know the resulting permutation is different. Okay. So what's the last thing I want to do today? The last thing I want to do today is talk about connections with matrices. Because we can really think about the group of permutations as a group of matrices. So why is this? Well, let's say that I'm working on S4. This means that I want to look at 4x4 matrices. So what's the association to a sigma, a permutation? Of 1, 2, 3, 4. And right, it's not every 4x4 matrix will be part of this symmetric group, but I want to see the symmetric group inside the group of 4x4 matrices. So how do I build a matrix? I build a matrix by saying, okay, right, the row corresponds to the image of the first basis vector. So here I want to put the sigma 1th basis vector. Then I'll put the sigma 2th basis vector. Sigma 3, sigma 4. Right, so for instance, the permutation 1, 2, well, 1 is sent to 2. Oops. So I put the second basis vector in the first column. 2 is sent to 1. 3 is fixed. And 4 is fixed. So this is 1, 2. So I build an association of a permutation to a matrix. And the way that matrix multiplication works, it says, okay, if I want to compute where the ith basis vector goes, I look at the output of the matrix will be the ith column. The third. So for instance, if I want to see where the third basis vector goes, the output of this matrix multiplication is going to be the third column, which is this one. And you can check that in general. If the output of the ith basis vector is the ith column of the matrix. So if I plug it into this one and the output of this matrix is sigma, and then I multiply it again by another matrix, pi, I'm going to take it to pi of sigma of I. So under this association, pi sigma is taken to the matrix for pi. Let me call the matrix for pi m of pi times the matrix of sigma. So this property is just like the sign property. Products are taken to products. And we'll talk about this before the end of the semester in more detail, what this property means and why it's important. But just know that this is a very special thing because it allows us to think about permutations as matrices, right? And instead of acting on the set 1, 2, 3, 4, it's acting on the basis vectors E1 through E4. The last thing that I want to talk about with matrices is the sign. The sign of a permutation, here, another nice way to compute it is just the determinant of the corresponding matrix. Which from this property and properties of products of determinants, you can recover the original property of sign that I've moved off the board now, moved away from the screen. Here. You can recover this property from this property in properties of determinants. It's just a very nice connection, and it shows why sign is important, right? Determinants we know are important, so the signs of permutations should be important as well. And they are important in applications. And really, they describe something very important structurally about the symmetric groups in general. And we'll talk about that well, I don't know if we'll actually talk about that, alternating groups and simple groups, but the sign is very important. Unfortunately, the book doesn't really go into detail about why the sign is important, at least at this stage. So I wanted to sort of justify why we were studying each of these things. Okay, well, I hope I didn't lose too many of you with this matrix stuff. I know that most of you have taken 220, so if you haven't taken it, I'm sorry, but I didn't want to neglect this analogy for those who had. You're not going to be tested on this. This is just an interesting side note that those who know some linear algebra will probably be interested in. Okay, good. So we will pick up again on Monday. On Monday, we'll continue with Chapter 4 and talk a little bit more about other algebraic structures that instead of generalizing groups, they're going to generalizing matrices with groups, they're going to generalize real numbers much more closely. So the prototype here is going to be the ZP, where you have not only multiplication, addition, but also multiplication and division. So we will talk about that on Monday. I hope you all have a great weekend, and I will see you then. Bye-bye.